Insulation resistance testing is crucial for 600 volts cables, including 4'4/0 American wire gauge copper THHN cables, as it verifies the integrity of the cable insulation. This test ensures that the insulation provides adequate protection against electrical shock and ground faults. It is a common misconception that megger testing can harm cable insulation. While high-voltage megger tests can potentially damage aged or defective insulation, proper testing using a megger rated for the specific cable type and voltage rating minimizes this risk. For 600 volts cables, an insulation resistance test with a megger rated for 500 volts direct current or higher is recommended. The test procedure should involve the following steps. Firstly, disconnect the cables from any equipment and grounding systems. Secondly, apply a voltage to the cables for a specified period, typically 1 minute. And thirdly, measure the insulation resistance between each conductor and the ground. The acceptable insulation resistance value for 600 volts THHN cables depends on the cable length and ambient temperature. For a 50-foot cable, an insulation resistance of at least 10 megohms is generally considered acceptable. Use a megger rated for 500 volts or higher for testing 600 volts cables. Limit the test time to 1 minute to minimize potential damage. Consider using a partial discharge detector during megger testing to identify any weak spots in the insulation. If the insulation resistance value is below the acceptable level, further investigation is required, such as visual inspection or a dielectric loss test. When performing insulation resistance tests, several factors must be considered to ensure accurate and reliable results. Firstly, cable preparation is paramount. Before commencing the test, thoroughly clean the cable surface to remove any dirt, moisture, or contaminants that could affect the readings. Ensure that the cables are energized and isolated from any connected equipment to prevent damage to the testing equipment or injury to personnel. Secondly, selecting the appropriate test voltage is crucial. While using a megger rated for 500 volts direct current or higher is generally recommended for 600 volts cables, it's essential to consult the cable manufacturer's specifications for the recommended test voltage. Applying excessive voltage can stress the insulation and potentially lead to premature failure. Thirdly, understanding the influence of temperature and humidity is vital. Insulation resistance values are temperature dependent, with resistance decreasing as temperature increases. Therefore, it's necessary to correct the measured values to a reference temperature, typically 20 degrees Celsius, using appropriate correction factors. High humidity levels can also affect the surface resistance of the cable, leading to inaccurate readings. Fourthly, interpreting the test results correctly is essential for assessing the condition of the cable insulation. The insulation resistance value should be compared against established industry standards or the manufacturer's recommendations. A sudden drop in insulation resistance over time may indicate insulation degradation or the presence of moisture or contaminants within the cable. If the insulation resistance value is below the acceptable level, further investigation is required. This may involve visual inspection of the cable for signs of damage, such as cracks, cuts, or discoloration. Additionally, a dielectric loss test can be performed to assess the overall quality of the insulation and identify any areas of weakness. In some cases, partial discharge testing may be necessary to detect localized defects in the insulation that could lead to eventual failure. Moreover, it's essential to document the test results meticulously, including the date, time, test voltage, temperature, humidity, and insulation resistance values for each conductor. This documentation provides a valuable baseline for future comparisons and can help track the performance of the cable insulation over time. Furthermore, safety precautions should be strictly adhered to throughout the testing process. Wear appropriate personal protective equipment, such as insulated gloves and safety glasses, to protect against electrical hazards. Ensure that the testing area is well ventilated and free from flammable materials. Follow lockout-tagout procedures to prevent accidental energization of the cables during testing. In addition to insulation resistance testing, other diagnostic techniques can be employed to assess the condition of 600 volts cables. These include time domain reflectometry, frequency domain spectroscopy, and partial discharge mapping. Time domain reflectometry sends a pulse down the cable and analyzes the reflected signal to identify any discontinuities or impedance changes that may indicate damage or degradation. Frequency domain spectroscopy measures the cable's response to varying frequencies of alternating current to assess the dielectric properties of the insulation. Partial discharge mapping uses specialized sensors to detect and locate partial discharge activity within the cable, providing valuable insights into the condition of the insulation. Regular insulation resistance testing combined with other diagnostic techniques can help identify potential problems with 600-volt cables before they lead to costly failures or safety hazards. By implementing a comprehensive cable testing program, facilities can ensure the reliability and safety of their electrical systems. In addition to the megger test, other methods exist for assessing cable insulation. Firstly, there's the high pot test, which involves applying a high voltage to the cable to verify its ability to withstand voltage surges without breakdown. Secondly, there's the tan delta test, which measures the dissipation factor of the insulation, providing insights into its overall quality and condition. Thirdly, there's the partial discharge test, which detects and measures localized discharges within the insulation, indicating potential defects or weaknesses. Each method offers unique advantages and limitations, making it essential to select the most appropriate technique based on the specific application and cable characteristics. Considering the environmental conditions is also vital during insulation resistance testing. Temperature and humidity significantly impact the readings, requiring adjustments to ensure accuracy. High temperatures can lower insulation resistance, while high humidity can create surface leakage paths, leading to misleading results. Therefore, it's essential to measure and record the ambient temperature and humidity levels during testing and apply appropriate correction factors to the measured values. Moreover, proper grounding techniques play a crucial role in ensuring safety and accuracy during insulation resistance testing. The testing equipment and cable under test should be properly grounded to prevent electrical shock hazards and minimize interference from external sources. A dedicated grounding electrode should be used, and the ground connection should be regularly inspected to ensure its integrity. Furthermore, understanding the limitations of insulation resistance testing is essential for interpreting the results correctly. Insulation resistance testing primarily assesses the overall condition of the insulation but may not detect localized defects or weaknesses. Therefore, it's essential to supplement insulation resistance testing with other diagnostic techniques, such as partial discharge testing, to provide a more comprehensive assessment of cable insulation. In addition to the technical aspects of insulation resistance testing, it's crucial to emphasize the importance of safety. Working with electricity can be hazardous, and proper safety precautions must be followed to prevent injury or death. Only qualified personnel should perform insulation resistance testing, and they should be thoroughly trained in the proper procedures and safety protocols. Personal protective equipment, such as insulated gloves and safety glasses, should be worn at all times, and lockout-tagout procedures should be followed to prevent accidental energization of the cables during testing. Ultimately, insulation resistance testing is a valuable tool for assessing the condition of 600 volts cables and ensuring the reliability and safety of electrical systems. By following proper testing procedures, considering environmental factors, and prioritizing safety, facilities can effectively manage their cable assets and prevent costly failures. Remember to always consult with qualified professionals and adhere to applicable industry standards and regulations when performing insulation resistance testing. In addition to the aforementioned points, consider the age and history of the cables being tested. Older cables may have degraded insulation due to environmental factors, thermal stress, or mechanical damage. It's essential to consider the cable's age, service history, and any known incidents or repairs when interpreting the insulation resistance test results. Cables that have been subjected to harsh conditions or frequent overloads may exhibit lower insulation resistance values than newer cables. Furthermore, ensure that the testing equipment is properly calibrated and maintained. Regularly calibrate the megger to ensure accurate readings. Faulty or improperly calibrated equipment can lead to inaccurate results and potentially misdiagnose the condition of the cables. Follow the manufacturer's recommendations for calibration intervals and maintenance procedures to ensure the reliability of the testing equipment. Moreover, when disconnecting the cables from equipment and grounding systems, take precautions to prevent accidental discharge of stored energy. Capacitive cables can store significant amounts of electrical energy, which can pose a shock hazard if not properly discharged. Use a suitable discharge tool to safely discharge the cables before commencing the insulation resistance test. Also, be mindful of the presence of other cables or equipment in the vicinity of the testing area. Ensure that the testing area is clear of obstructions and that other personnel are aware of the testing activities. Use barriers or warning signs to prevent unauthorized access to the testing area and minimize the risk of accidents. Finally, consider the potential for electromagnetic interference during insulation resistance testing. Nearby electrical equipment or power lines can generate electromagnetic fields that may affect the accuracy of the test results. Shield the testing equipment and cables from external electromagnetic interference to minimize its impact on the readings. Additionally, use shielded test leads and follow proper grounding techniques to reduce the effects of electromagnetic interference. By taking these additional factors into consideration, you can enhance the accuracy and reliability of insulation resistance testing and improve the overall management of your cable assets. Let's delve deeper into the interpretation of insulation resistance test results. It's not just about meeting a minimum megohm value. The shape of the curve when plotting resistance over time can tell you a lot. For example, a rapidly decreasing resistance reading indicates a significant insulation problem, while a stable or slowly increasing reading suggests the insulation is in good condition. This is often referred to as a polarization index test. The polarization index is the ratio of the resistance reading taken at 10 minutes to the resistance reading taken at 1 minute. A high polarization index, typically above 2, indicates dry and relatively clean insulation. A low polarization index, often below 1, suggests the insulation is contaminated or has absorbed moisture. This is because clean, dry insulation polarizes over time, leading to a higher resistance reading after 10 minutes. Contaminated or wet insulation, on the other hand, will not polarize as much, resulting in a low polarization index. Another important consideration is the dielectric absorption ratio. This is similar to the polarization index but uses resistance readings taken at different time intervals, usually 60 seconds and 30 seconds. The dielectric absorption ratio provides additional information about the condition of the insulation and can help differentiate between different types of insulation problems. Furthermore, it's crucial to consider the specific type of insulation used in the cable. Different insulation materials have different dielectric properties and will exhibit different insulation resistance characteristics. For example, cross-linked polyethylene or XLPE insulation typically has higher insulation resistance values than polyvinyl chloride or PVC insulation. Therefore, it's essential to compare the measured insulation resistance values against the manufacturer's specifications for the specific type of insulation used in the cable. In addition to the polarization index and dielectric absorption ratio, other diagnostic parameters can be derived from insulation resistance test data. These include the dissipation factor, capacitance, and inductance of the cable. The dissipation factor is a measure of the energy lost in the insulation due to dielectric losses. A high dissipation factor indicates poor insulation quality or the presence of contaminants. Capacitance and inductance are electrical properties of the cable that can be affected by insulation degradation. Changes in capacitance or inductance over time may indicate insulation problems. By analyzing these diagnostic parameters, you can gain a more comprehensive understanding of the condition of the cable insulation and identify potential problems before they lead to failure. Finally, remember that insulation resistance testing is just one tool in a comprehensive cable management program. It should be used in conjunction with other diagnostic techniques, such as visual inspection, partial discharge testing, and thermography to provide a complete assessment of cable condition. Regular inspections, maintenance, and testing can help ensure the reliability and safety of your electrical systems and prevent costly downtime.